Hi guys, Mr. Rocco here. Hope you're having a good weekend. We are working on the second portion of topic 5, which is climate. So we covered weather. Last week was the weather test, and now we're going to cover climate. That'll take us about 2 weeks, this week and next week. And then that'll be it for this unit. So let's jump right in and talk about the mountain effect, or it's called the orographic mountain effect. This was something we've covered already, but just a little review. So clouds, right? Clouds form from the process of condensation. And in order to have air condense, you have to have all of this first part happen. The warm air at the surface, right, where the heat comes out of the ground. Let's say this is the ground and the infrared heat's coming out. And now you've got all this warm air down here on the surface. You then start that whole process of convection where the cold air way up high is going to push down, sink down, and then push underneath warm air. As that air rises, it then does all of these things. So as it rises, it expands, it cools, and it condenses. So all of that happens as air is going up. As it's rising, it's expanding, cooling, and condensing, and eventually forming clouds. The opposite happens to air that sinks. Sinking air, as it's coming back down, the pressure is increasing, and so the molecules are compressing. They're getting forced together. That's going to create a lot of friction, which creates a lot of heat, and the temperature of the air mass actually gets warmer. Warmer air does not create clouds. So this first thing here where it rises, expands, cools, and condenses, that's where you're going to get clouds. And then the second thing, where the air sinks and compresses and gets hotter, you're going to get no clouds. And that is going to happen on each side, 2 different sides of the mountain range. So on a mountain range, especially large mountains, you're going to have that situation where one side of the mountain range tends to be cooler and more cloudy and a lot more precipitation, snow and rain. And on the other side, it tends to be warmer and drier and less rain, less precipitation. So they call it the orographic effect, which is the effect that large mountain ranges have on the weather. These are some examples in the United States. We have the Sierra Nevadas, which are out west. I'll show you a map in a minute of where their location is. The Rocky Mountains and the Cascades up in the northwest part of the United States, up by Seattle, Washington. This map shows where these are 5 examples. So the Cascades sit up here in the state of Washington and Oregon. That's where you're going to see this mountain effect happen. The Sierra Nevadas, right here, number 2, that's going to be on the border between California and Nevada. You have the Rocky Mountains, right here, number 3, Colorado, Utah, place like that. You have the Black Hills of South Dakota, where Mount Rushmore is. Those are the Black Hills. You could see this mountain effect. And the Appalachians, which come all the way down here toward Georgia and then run all the way up actually into New England. So you can see that effect here, especially in this part of the Appalachians, North Carolina, Tennessee, parts of Virginia, West Virginia, Kentucky. You're going to see that mountain effect. So those are 5 areas of the country where you might see this effect. So this is showing you a mountain range. Now again, in the United States, storms go west to east, and that has to do with the planetary wind belt. So again, that's on, if you go to your reference table on page 14, there was a question on an assignment last week that a lot of students missed, and I kept giving a hint to look on page 14. In the United States, because we sit in a certain latitude, we're between 30 degrees north and 60's way up here in Canada. Because we're between 30 and 60, we sit in what's called the prevailing southwesterlies. That means everything goes, winds are going southwest to northeast, like that. So generally, storms are going west to east. And so in the United States, the west side of the mountain range is called the windward side. And it's easy to remember because they both start with W. That's how I keep it straight in my head. So the western side of a mountain range in the United States is the windward side. Now, that's not going to be the case all over the world. It's whatever side the wind is hitting is the windward side. It just happens to be that in the U.S., it's on the west side. There are other latitudes and other wind belts. Some come from the east. So in some other countries, the windward side might be the eastern side of the mountain if the wind's coming, let's say, this way. But that's not the case in the United States. So just keep straight that in the United States, west is the windward side. So the air's coming this way. Well, when it gets here, it's like hitting a brick wall. It has only one place to go. As it's coming across from the west and heading east, it hits this side of the mountain range, and now the air gets forced up the mountain. Well, now you start doing all those things that we mentioned in the first part there. The air has to go up. So that's rising air, which causes it to expand. As it's expanding, it's getting cooler, and you're going to get clouds. So typically on the western side, you're going to see a lot more clouds over here, which of course are going to give you rain and snow and all kinds of precipitation on the west side. So the western side, or the windward side, is always going to be the cooler, wetter side of the mountain range. Then you come down the mountain on this side, and you have the opposite effect. There's the sinking air. So the air is coming down the mountain on the east side. The eastern side is called the leeward side, L-E-E-W-A-R-D. Again, the way I remember this one, I use the E's. Lee has two E's, and stress that the word east has an E, right? Starts with E. So the eastern side is the leeward side. The western side is the windward side. Again, this is in the United States. Again, other parts of the world, it might be different. So on the leeward side, the air is sinking. It's going down the mountain, and that's just the opposite. So on this side, it was rising and expanding. This side, it's sinking and compressing. The molecules are getting forced together, and so there's going to be a lot less clouds. It's going to be dry. It's going to be much warmer. The pressure on the air is going to increase, more friction. So the molecules are going to smack together, which creates more heat. So the air tends to be a lot warmer on this side. I have had students in past years, they've gone out to ski or snowboard, let's say out to Colorado, and they will travel up and down the Rocky Mountain Range. And I've had kids, I haven't seen this personally. I wish one of these days when I get out west. But if you've been out there, maybe some of you have, if you're on the western side of the Rockies, you might, and I've had students say, "Oh, Mr. Rocco, I've been on the western side of the mountain range, and it was snowing, and it was cold. It might have been in the 20s, a lot of snowfall, great skiing on this side of the mountain range." Then they left the ski resort, traveled up over the mountain range, and went to the eastern slope on the leeward side, and the temperature went from 20s over on the west side to like 60s over here. And it was sunny. It almost went from like winter to spring just by going up and over the mountain range. They went from 20-degree temperatures over here to 60s and sunny and dry on the leeward side. And you can have drastic differences just by going up and over a mountain range from one side to the other. So again, personally, I haven't seen that up close, but I've had many students that have taken trips out west and have seen this. So it's really cool. This shows the same thing here. So you can almost see the dividing line is like the peak of the mountain range. And you've got on the west side, this would be the windward side over here, where the air is coming in, and it's lifting up, and that's creating all that rising air, expanding, cooling, condensing. You see you've got a lot of clouds, a lot of rain. It's going to be moist. It's going to be cool. And then you get to the other side, the downslope side, where the air is coming down the mountain, and you've got much warmer, drier, desert-like conditions. Yep, desert-like. So you could have two drastic climates just because of the side of the mountain you're on. Western side, windward side, it's cool and wet, and the eastern side tends to be warm and dry. Now, there is a mathematical way to figure out the elevation, or the altitude at which a cloud forms. So we're going to get into that now. And in order to find where a cloud would form, you need to figure out the dew point temperature. And this is something we've covered. This is the definition of dew point, which you should know. The temperature at which the air temperature has to cool to reach 100% saturated. So when the air, again, this is something we've talked about, when the air temperature equals the dew point temperature, when they reach the same number, that's when the air is saturated. That's when you've reached 100% humidity, and that's when condensation starts. So the dew point temperature is reached as the air is rising. Because again, as air rises, let's say this is the ground, the air is going up. It's going up and expanding. It's going like this. The molecules are spreading out from one another. And somewhere up here in the atmosphere is where these two numbers are going to equal. And that's when you're going to start to form a cloud somewhere up here in the atmosphere. So the key here is to look for this. When the air temperature equals the dew point, that's when clouds will start to form. And we need this information to use it to figure out the base of a cloud. And let me show you that. So in order to know where a cloud's going to form, I'm going to go through this mathematical calculation here. It's not hard, but I'll try to go through it slowly. There are what are called lapse rates, and these are rates for different types of air. So you've got 3 types of air masses. You've got dry air, which means no water in it whatsoever. You've got moist air, which is, let's say 50% humidity. So we'll call dry air 0 humidity. Moist air is 50% humidity. And then you've got dew point air, which is 100% humidity, totally saturated. Notice the number gets lower as you go up in humidity. That goes back to, again, when we covered water and specific heat. Water holds on to its heat. Water has a high specific heat. Takes a long time to heat up, but remember, it takes a long time to cool down. Again, boil water. Get a pot of water, boil it on the stove. It takes a long time to get the water to boil. Shut the stove off. The water cools slowly. And so that's why the numbers get lower. So if you're talking about air without any moisture in it, it changes rapidly. Dry air will heat up quick, but also cool down quick. Best example, that would be a desert. Again, people think, oh, you can't freeze in a desert. That's not true. Many of you probably know this already. You can freeze in the desert very easily at nighttime, right? So places like Arizona, New Mexico, that get extremely hot during the day when the sun is out, their temperatures can drop dramatically at night once the sun goes down, because a place like Phoenix and those dry areas have no water to retain any kind of heat. And so their temperatures change quickly. So dry air is going to change its temperature 10 degrees. That's a pretty high number. Every 1,000 meters. That kilometer is 1,000 meters. Right? So every kilometer you go up, dry air will drop 10 degrees. And every kilometer you come down, it will go up 10 degrees. Now, again, once you throw some moisture in the air, that number goes down a little bit because, again, water holds on to that heat. And so instead of 10 degrees, now the temperature is only changing 6 degrees per kilometer. Still fast, but not as fast as totally dry air. And then you get your saturated air. Again, this is air that has a ton of moisture, 100%, totally saturated. Notice the number, only 2 degrees, very little fluctuation. That goes back to the last lab we did talked about San Francisco versus Kansas City. And many of you got that right. San Francisco being on the ocean, their temperatures don't fluctuate that much because they're next to a large body of water. So coastal cities, their temperatures stay a little more steady. They don't get as hot in the summer and they don't get as cold in the winter because of that water influence, because they're next to the ocean. So here's that water influence. Only 2 degrees. Dew point air only changes 2 degrees every time you go up a kilometer and 2 degrees every time you come down a kilometer, up and down a mountain, let's say. So we've got 10 for the dry, 6 for the moist, 2 for the dew. So we want to remember those numbers, 10, 6, and 2. Now, what we're trying to do here, if I'm totally confusing you, is we want to figure out at what level, what altitude, I'll put ALT, what altitude is a cloud going to form? I'm looking for the base. Clouds form as the air goes up. So the first thing to form on a cloud is the bottom of the cloud. They call it the cloud base, and then the clouds will kind of blow up like this. They'll kind of puff up as they rise up, 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 up. So we're looking for where the cloud base is. And what we're looking for, and again, is when the air temperature equals the dew point temperature. When the air equals the dew point. So I listed the steps over here. Let me reset this. Okay. What you want to do, and you would have to know this, you got your mountain here. Okay. We've got sea level, which is 0 kilometers. Then we've got 1 kilometer, 2 kilometers, 3 kilometers, 4 kilometers, 5. This is pretty tall, very tall mountain, 5 kilometers high. The wind is coming from the west, so the wind's coming this way, right? This side of the mountain is the windward side. This side of the mountain is the leeward side, right? This is the west side. This is the east side. Okay. They have to give you these two numbers. So you have to know what is the air temperature at the base of the mountain, and this is in Celsius. You can see it's a warm day. It's 30 degrees Celsius. And the dew point temperature is 14 degrees. And then these are the steps that you go through to figure out where the cloud's going to form. So let's go through step 1. The first thing you do is the dew point number, because that's really easy when you go up and down the mountain. So dew point up, dew point down. So the dew point number, I wrote them up here in the top right corner. These are those lapse rates I just went over. Dew point, because the air is totally saturated, changes 2 degrees per kilometer. As you go up each kilometer, you take away 2 degrees, and as you come down the mountain, you add 2 degrees. So it's pretty easy. So if this is 14, you're just going to subtract 2 each time you go up another kilometer. So 14 minus 2 is 12. 12 minus 2 is 10. 10 minus 2 is 8. 8 minus 2 is 6. And 6 minus 2 is 4. So at the top of the mountain, the dew point, I'll put DP, is 4 degrees. That's Celsius. Then you come down the mountain, it's mirror image. Now you're going to add 2 degrees. So if this was 4, this is 6. Add 2 more, 8. Plus 2 is 10. Plus 2 is 12. And plus 2 is 14. So you see you've got a mirror image, right? The numbers on each side at the same level are the same. Very easy. That's the easy part. Step 2. The air down here at the bottom of the mountain on the west side, over here where I'm kind of hovering my mouse, is the air temperature. This is considered dry air. So you start with air at the base of the mountain. There's no cloud down here. You're going to use the dry rate until you hit a cloud. And again, how do I know when I hit a cloud, Mr. Rocco? When the air temperature equals the dew point, then I have a cloud. So I got a 30-degree air temp here, and I'm looking at the dry rate. So I'm going to use this number way up here, 10 degrees per kilometer. I'm going to go up the mountain. I'm going to subtract 10 until I see an equal here. These two numbers, the air and the dew, are equal. So if this is 30, 30 minus 10 is 20. Then I ask myself, okay, is 20 equal to 12? Nope. Keep going. Subtract another 10. I'm using the dry rate. 20 minus 10 is 10. Bingo. 10 equals 10. So that means at 2 kilometers right here, I'm going to put the base of the cloud, and I've got myself a cloud. And I'm going to have rain or snow or whatever kind of preset. Well, it's 10 degrees Celsius, so that's way above freezing. So it's going to be rain right there. But I've got a cloud forming at 2 kilometers up. Now, once I have a cloud, the air now is condensing. So the air isn't going to be dry anymore. Now I've got moist air. So you see here, I did step 1 was dew point, step 2 was dry. I switch now from the dry rate to the wet rate or the moist rate. And the moist rate is up here in the top right is 6 degrees. So I'm still got this 10 Celsius. I'm going to subtract 6 as I work my way the rest of the way up to the top of the mountain. So 10 minus 6 would be 4. 4 minus 6 would be negative 2. And negative 2 minus 6 would be negative 8. I kept taking away 6 each time because I've got moist air as I go the rest of the way up the mountain. So at the top of the mountain, the air temperature is 8 below Celsius. Now, once you get to the top, this is where it gets a little tricky. As the air goes up and over the mountain, this is almost like a wall right here, the peak of the mountain. The air is going to start to get forced down the mountain. What tends to happen is most of the moisture gets left over here on the windward side. Remember I said it earlier, the windward side is the wet side. This is where the moisture is going to get left. This side, the air really starts to dry out as it's compressing. It's like squeezing a sponge, right? You got a sponge that's sopping wet, and then you take your hand and you squeeze the heck out of it until all the water's, you wring all the water out of it. So this side of the mountain, you're going to switch back to the dry rate. And you see over here, that's step 4. So the dry rate was 10. So I'm going to add 10 each time I go a step down here. Starting at the top of the mountain was negative 8. So negative 8 plus 10 would be, what, plus 2? 2 plus 10 is 12. Plus another 10 would be 22. Plus another 10 would be 32. And finally, over here, 42. Now, you say, wow, that was a lot of steps. Let me review. First thing you did was the dew point. I subtracted 2, minus 2, minus 2, minus 2, minus 2. Add the 2, plus 2, plus 2. Then I did the dry rate, 10. I said 30 minus 10 is 20. 20 minus 10 is 10. Oops, I got 10 equal to 10. There's a cloud. Then I went to the wet rate, minus 6, minus 6, minus 6. And then I added, I went to the dry rate again, plus 10, plus 10, plus 10, plus 10, plus 10. If you go back to the beginning of this video, let me go back for a sec. Remember I said that the windward side is always cooler and wet. The leeward side is always drier and warmer. That's what you want to look for. You want to look at your air temps. It was 30 degrees on the cooler side, the windward side. It was 42 degrees on the leeward side. This number over here on the leeward side should always be greater than what you started with. In this case, it's 12 degrees. It doesn't have to always be 12. It just has to be higher. Can't be lower, can't be equal. This number should always be greater than what you started with back here on the other side of the mountain, because this side's always the warmer side, and this side's always the cooler side. So in this case, we did it right. If this number came out lower, then somewhere in here we messed up. Okay. This just summarizes what we did. So we did the dew point first. We did the dry rate next, 10 minus 10 minus 10. We had a cloud right here at 2 kilometers. We switched to the wet rate, minus 6, minus 6. We got to the top. Remember, it was negative 8. We then switched back to the dry rate, adding 10 all the way down, and we got that 42, showing it was warmer on the windward side than it was on, warmer on the leeward side, cooler on the windward side. This just shows, again, this would be, if I split the mountain range right down the peak, right? You've got a lot of cool, wet conditions on the windward side. You've got a dry, desert-like condition on the leeward side, warmer. This just shows the same thing. Notice all the clouds, and it's cool over here. And notice it's desert-like on the leeward side. This is actually a satellite image of the island of Hawaii. And you can see the peak of the mountain is right here. So you've got a mountain range right here, this little peninsula that kind of sticks out on the north end of the island there. And a good question, which I would, if I were writing a question for the Regents, would be to draw an arrow to show the wind direction, which way the wind is coming from and heading toward. So if you recall that the windward side is always going to be the side that is cooler and wet and a lot more moisture, and the leeward side, the downslope, is the side where it's drier, right? Then which way would the arrow have to be facing to show which way the wind direction is? So you're looking down on a mountain here. There's the peak. So hopefully, if you're thinking about this clearly, the arrow would have to go like that, right? Because this side of the mountain would be the windward side, right? Notice it's much more lush green. You've got clouds over here, right? Then this would be like lifting up. This would be the peak of the mountain. And then this is the downslope side on this side where you can see it's much more dry. You got that brown color to show the desert. So that would be a good question on the Regents, just to ask students to, they would probably label this a mountain. They might even draw a line here and write, this was the peak of the mountain. They'd say, this is the peak. You're looking down on the mountain on Hawaii. Draw an arrow to show the wind direction. So you'd have to put an arrow going like that, coming out of the northeast, heading southwest. This is actually looking now from the ground level. This is the same big island of Hawaii, but now you're on the ground level. So this is that windward side, which was over here. And this is the leeward side of that island. So you can see, right, very, very dry compared to the windward side where it's all wet and tropical. Yep. Another place you're going to see this again are the Cascades. So if you go up to the northwest United States, right here in this little, I put like a pink color here. These mountains right here, these are called the Cascade Mountain Range. They go through the state of Washington, actually go all the way down Oregon and even into Northern California. So they'll extend down this far. You have Seattle, Washington, which sits on the windward side because the winds are coming in off the Pacific Ocean. And you've got Spokane, Washington, which sits on the leeward side. And what you're seeing here are actually the temperatures and precip conditions yearly for Seattle and Spokane. Temperature-wise, you can see this red line is your temperature. They both have that bell shape like we do. Cool in the winter, it gets warmer in the middle of the year. This would be July, August, right? It's warm, and then cool again. But notice the peak. Spokane gets a lot warmer. In fact, the peak of the temperature graph hits that 68. It doesn't even, get close to 68s in this range for Seattle. So Seattle is definitely cooler, being on the windward side. Rainfall, you can see the blue bars show you rain amounts, right? Seattle gets a ton of rain. So Spokane gets some rain, but you can see these blue bars are not even close to the height of these bars. So again, much, much cooler and much, much more moisture on the Seattle side, the windward side of the mountain range, the Cascades, whereas Spokane is definitely a warmer, drier side of the mountain. This also shows two other places in the state of Washington. So you have Tacoma, Washington. The Cascades are right in this area, right where this black line right here. This would be the Cascades. And you can see on this side, Tacoma. This is the Pacific Ocean over here. So you get the winds coming in off the west, coming from the west, heading east. Tacoma gets 40 inches of rain a year. Over here on the other side of the Cascades, again, the Cascades are here. You got Yakima. Yakima gets about 8 inches. So Tacoma gets 5 times more rain than Yakima gets, right? So it's much, much wetter and cooler over here than it is on this side of Washington state. So just to kind of sum up here, the windward side, the air is rising, expanding, cooling, and condensing to form clouds, right? You get a lot of rain and a lot cooler conditions on the windward side. And then the leeward side is the opposite. The air is forced to sink. It's compressing. It's going down the mountain. Right? There's your mountain range. So it's coming down the mountain. It's sinking. It's compressing. It's getting hotter. It's heating up. And it's drying out. All on the leeward side. Which again, in the United States is always going to be the eastern side of our mountain ranges. And the western side is always going to be the windward side in the United States. Okay. What I want to do is one more of these examples of a mountain to figure out the cloud base. Excuse me. The only difference with this one is going to be, remember the rates were, the dry rate was 10, the moist rate was 6, and the dew point rate was 2. That's per kilometer, right? This mountain has levels here. You see these lines is using every half kilometer. Kilometer is 1,000 meters, but you can see on this particular mountain, this goes 500, then 1,000, then 1,500, 2,000, 25. So what I have to do here, I'm using the same procedure, but I took these numbers and I cut them in half. So the dry rate was 10. Instead of 10, I'm going to use 5 because it's every half kilometer. The wet rate was 6, but I'm going to cut it in half, so now it's 3. And the dew point rate was 2 degrees per kilometer. Now I'm just going to use 1. So I'm doing the same steps, but I'm using half the rates. Because I'm not a kilometer, I'm at half a kilometer. And again, the first thing you want to look for is you've got to have your dry bulb number is your air temp. Remember, dry bulb is just a regular thermometer. So that's your air temperature. It's 22 degrees. And your dew point is 10. So again, the 4 steps were, 1, start with the dew point. I'll just kind of list them here. 2, use the dry rate until you hit a cloud. Then switch to the wet rate till you get to the top of the mountain. And then go back to the dry rate on the right side or the eastern side of the mountain when you come down. So let's do the dew point rate first. Now remember, we're using 1 instead of 2 because it's half a kilometer. So if the dew point is 10, as I go up each level here, I'm just going to take 1 away. So 10 minus 1 is 9. This will be 8, 7, 6, 5, 4. So at the top of the mountain, the dew point is 4 degrees. I'll put DP. All right. Now I go down the mountain, I just add. So add 1. 5, 6, 7, 8, 9, 10. So again, mirror image on either side. That's easy. Cross that off. Dry rate. I got 22. Again, it's 10 for every kilometer, but now we're going to do 5 because it's half a kilometer. So I'm going to subtract 5 until I have equals. And somewhere I should hit an equal here. The dew point in the air should equal. So 22 minus 5 is 17. Is 17 equal to 9? Nope, keep going. 17 minus 5 is 12. Is 12 equal to 8? Nope, keep going. 12 minus 5 is 7. Is 7 equal to 7? Yep. Where's my cloud? 1,500. 1.5 kilometers. So right here, I had to put a base of a cloud. Make a little cloud. I'm going to have rain. Got precipitation. The air is now condensed and is moist. Okay. Now I'm done with the dry rate. I switch to the wet rate until I get to the top. The wet rate again was 6, but in this case, I'm going to use 3 because it's half. So I got 7. 7 minus 3 is 4. Next level, 4 minus 3 is 1. One more level, 1 minus 3 is negative 2 Celsius. So at the top of the mountain, that's my air temp, is negative 2 Celsius. Now coming down the mountain, cross that off, I got the dry rate. Because I'm going down the mountain, the air is sinking and compressing, so I'm going to go back to the 5 degrees. The dry rate is 5. I'm going to add. Negative 2 plus 5 is 3. 3 plus 5 is 8. 8 plus 5 is 13. 13 plus 5 is 18. 18 plus 5 is 23. And 23 plus 5 is 28. Hopefully I did that correctly. And then I check. Is 28 greater than, all the way back over here, 22? Yes, that means I did it right. This number should always be higher than what you started with back on the other side of the mountain range. So I know that I had rain. I know I've got cooler numbers on the west side, the windward side, over here. And I know on the leeward side, I don't have any rain. Notice none of these equal, right? They shouldn't. I don't have any equals. And I've got a warmer temperature here. Okay, that is it for this video. So please go back, rewatch if the parts about the mountain don't make sense. Go back and watch them again. And there'll be a worksheet to do that goes with this video. And I will talk to you soon. Bye.